redo calculations and correct for this overestimation to hopefully get a better fit for data.
Okay, please join me in thanking Stephen. We can be interrupted because Zoom meeting was set up for 2 hours. So let's thank both Stephen and all presenters. But in case we didn't get interrupted, we can go to the question section. But do not be surprised if by some reason something happened. So we made everything in time. So there is a question from Professor Han Huang. It should be alpha-ruthenium chloride, isn't it? I don't think alpha-ruthenium chloride is stable.
Yes, it's alpha-ruthenium chloride 3. I'll back up a bit. Yeah, we have in total 2 ruthenium atoms and 6 chlorine atoms in our unit cell. The reason it's missing a subscript is just a formatting issue with writing this.
Okay. Next question from Professor Han Huang. Is ruthenium 3 plus in high spin or low spin configuration?
Should be low spin.
I would agree. So how many unpaired spins on one ruthenium?
There are 1.
Okay. And on behalf of Professor Han Huang, I would ask, did you try for MEG, for magnetization value in the Aussie car? Does it show for ferromagnetic 2, which would be 2 spins, or okay? So it is confirmed. More questions to Stephen? Yep, please.
Stephen, can you go to this comparison between your data and some experimental data, right?
Which has both have peak at 100 Kelvin, right?
I'm a little bit confused. So this is the data. This was already from some paper, right?
Yes.
And which would be good idea actually to cite the paper on your, since you're showing the data from someone else. It would be a good idea to really refer to the article which you are taking this data. But there's also the red line corresponds to the modified Abaniccia model. Can you give a little bit more ideas about how, and it looks like you said, oh, our data are really not so good, but I think they correspond in 100 Kelvin. Well, if your scale is in Kelvins, right? Yes. Your temperature is in Kelvins, I hope, not Celsius. So your 100 peak is kind of increasing, and they have the peak on 100, and then it's going down, which also follow in your predictions. I think the only disagreement is in a very low range of temperatures around less than 10, right? Which looks like logarithmic scales. I don't know exactly what is the temperature where they have this peak. And in your case, looks like you really have 0 instead of a peak there, right?
Yes.
So it's really disagreement in this very low temperature range. Can you give a little bit more ideas what exactly is different from your, and I think it's really difference in approach, which provides this difference in this low energy disagreement. What exactly?
Mine negative?
Yeah, what exactly different in their approach, Abaniccia approach, compared to yours?
I don't recall it exactly from the paper. It's been a while since I've read it, but I think the issue with that would be is that I used a collinear method and they used a non-collinear method. Since
what does it mean? Please explain.
One of the leading theories of what causes that large spike you see at about 8 Kelvin on the experimental data is that there is an interaction that arises from the off-diagonal components of the electron density, and that by using a collinear method, we ignore that and treat it as non-existent. And so that would obviously dramatically impact the results.
And why it's not so important for 100 Kelvins for the high temperature regime?
Oh, because that effect disappears at high temperatures experimentally, which is why it drops precariously in the experimental.
But it's still present at 100 Kelvins. But your theory provides this peak at 100 Kelvins, but doesn't provide in low temperatures, right? So like these collinear, non-collinear calculations looks like they probably not so important when you go to 100 Kelvins. Any idea why? Honestly, I don't know the answer. I mean, I have a few ideas, but
if I had to speculate on why, it'd be that well, obviously, as we get in higher temperatures, we have higher energies in our unit cell, and the effects that are leading to this deviation we see are less prominent, simply because they don't scale at the same level. They, as the temperature gets higher, the ability for the spins to flip against the magnetic field increases, the probability increases, and the overestimation of our interaction becomes less important.
okay.
So, Stephen, what you've told about spin flip, spin degrees of freedom contribution to heat capacity corresponds to the peak at 8 Kelvin. But what is the nature, which degrees of freedom contributes to the peak at 100 Kelvin? So in your modeling, you run molecular dynamics, which means you enable motion of nuclei, right? Nuclear degrees of freedom or oscillations of nuclei around. Does it have any relation to the second peak?
It could. Unfortunately, I was not able to get the program for making a video out of the molecular dynamics calculations to work. So I wasn't really able to look on that.
But you can hypothesize that likely the second peak originates from activating some interatomic vibrations. So it would fit the Einstein or Debye models for heat capacity.
Yes.
So it's not magnetic nature, it's just oscillations in solids. Okay, more questions to Stephen? More questions one? More questions two? More questions three? So let's thank Stephen once again. You can stop sharing. And Stephen, yes.